All right. So welcome everybody. My name is Samuel Horvad and I'm one of the co-organizers of the FlOW seminar, together with Peter Richtarg, Virginia Smith, Avralin Belets, and Dan Alistair. So a few admin things before we start. So this talk going to be recorded and it will be available on our YouTube channel afterwards. So FlOW seminar stands for Federated Learning One-Word Seminar that provides a global online forum for the dissemination of latest scientific research results in all aspects of federated learning. This includes distributed optimization, learning algorithms, privacy, cryptography, personalization, communication compression systems, hardware, and for instance, new generation of models. Today, it's my pleasure to introduce you Steve Laskaridis, who is a research scientist at Samsung AI Center at Cambridge, UK. Prior to that, he obtained his MS degree with distinction in advanced computer science from University of Cambridge. And today he's going to tell us about heterogeneous federated learning. With respect to questions, Steve agreed to take questions throughout his talk. So there are two ways how you can ask the question. So either put your question to chat and set visibility to everyone, or just raise your hand and then we will try to unmute you so you can ask your questions in person. Right, so that's everything. So please, Steve, the floor is yours.
Thanks a lot. Thanks, Sam, for the introduction and the invitation. So I'm Stefanos, or Steve, as you heard, and I'm going to present your work on federated training with ORdered Dropout for tackling system heterogeneity with a system called FjORD. Introductions first. I'm Stefanos. I'm from Greece, and I'm an ML researcher at the Distributed AI group of Samsung AI Center in Cambridge. Previously, I did my master's in the University of Cambridge, and I was also before that an engineer at CERN in Switzerland. My research interests revolve around the areas of distributed and mobile systems, federated learning, of course, especially since I'm here, and ways to deploy efficient deep learning models on resource-constrained devices such as mobile or embedded systems. So this is roughly the outline of my talk. I will start with a brief introduction on embedded and mobile DNN training and federated learning and its challenges, both with respect to heterogeneity and other system deployment challenges. Next, I will go through how existing work tackles this and where they fall short. Subsequently, I'm going to present what we did with FjORD by first introducing our ORdered Dropout technique, and then how this is applied in the federated training setting. Next, we'll present our evaluation results and illustrate how FjORD fares with respect to the state of the art and how it behaves across different settings and scenarios. Last, I'm going to go through some of the limitations of our system and future research directions. So let's first talk about the state of deep neural network training on mobile and embedded settings. It is a fact that DNNs have been getting more and more accurate at the expense of also getting deeper and wider. Although advances in hardware accelerators have enabled training and inference at scale, the current trend of models of larger footprint undoubtedly affects their deployability in the mobile setting. Given the latest trends of mobile SoC design and user privacy prioritization, on-device training has gained momentum to drive a movement of the training process closer to the sensors. Thus, the question here is shaped to be on how can we migrate from on-device inference-only scenarios to on-device training. Training on device arguably needs more compute, memory, and energy requirements due to the extra computation and data structures to be kept. And towards the goal of mobile on-device training, architectures, optimizers, and toolsets are hardly prepared. So, of course, towards this goal of on-device training, one needs to take into consideration the device landscape, which has always been very heterogeneous, be it in terms of computational capabilities, memory size, battery capacity, or even thermal dissipation. In fact, in the wild, one can find various devices of different form factors, TDPs, and equipped with different SoCs spanning across different device tiers and generations. Last, these devices support multitasking, and thus the external workload coming from various applications can vary dynamically. So the question is on how can we effectively support on-device training across these heterogeneous targets. There is the distributed paradigm of training through federated learning, which is a new privacy-centric paradigm for learning that moves training closer to the data. You can see a metaphorical visualization of federated learning here, with the clients being represented as islands found in a pool of data and coordinated by the cloud. Of course, giants like Google, Apple, and Samsung are hidden behind the clouds in this picture. But in more literal terms, federated learning looks like this. Typically, you have a server hosting a potentially pre-trained model, and at each round, it samples certain clients out there and transmits the global model to them. Clients train on their local dataset, probably under non-IID settings, and it's tackling a slightly different task potentially. Then they send back the updated models to the server, along with some extra metadata, such as, for example, the number of examples that they trained upon. Then, depending on the aggregation scheme, the server merges these gradients and updates the global model for the next round until convergence. Of course, this can be a long-running process where new information is constantly integrated, for example, see lifelong learning, and the goal might not only to have a globally good model that behaves well across targets, but also making good personalized local models for the clients. We're focusing in this work on in the former case with a massively distributed set of clients and not the siloed version of federated learning. So even under the desire to create a globally good model by leveraging the local device datasets, one does not really walk into models like this. So federated learning comes with certain baggage in terms of heterogeneity, namely data and system heterogeneity. On the one hand, data on clients can follow non-independent or identical distributions, which might hurt convergence and accuracy. Also, from an optimization perspective, it can lead to different objectives between the server and different clients, like their optimization goals be essentially having discrepancy between the optimization goals. On the other hand, nor the devices in the wild are homogeneous, as aforementioned. There are different tiers and different generations of devices out there with different compute memory and networking capabilities. This can lead to stragglers or fairness issues if slower devices are consistently dropped and not being accepted in the training process. Also, it has been shown that correlations between population demographics and device capabilities might exist, leading to further biases in training. So system challenges in federated learning can largely be classified in three broad categories. The communication-specific challenges with respect to broadcasting the global model to participating devices and getting the updates back from them. Then it's the local compute dynamics in terms of the device capabilities, training latency, memory consumption, or even energy. And then there is the scalability and fault tolerance. The scalability and fault tolerance part of the system. So there is a scalability and fault tolerance part of the system that, of course, can be an obstacle in the training process of the distributed system. So, of course, these challenges can potentially be tackled in a complementary way, such as, for example, having a model compressed, which can lead both to memory and transfer gains. The same can be argued for minimization of latency, for example, and the probability of a failure coming up. So how do existing solutions go about tackling these issues? The first family of approaches springs from centralized training and are techniques that aim to bring down the computational cost of training or inference. Such techniques include random dropout, which is not really aimed at that, but I'll come back to that later. Weight or channel pruning, hand or NAS-tuned DNN designs, architectures, such as mobile nets or efficient nets, quantization, and low precision training, as well as knowledge distillation. These approaches are largely complementary to what we're proposing and, to be honest, orthogonal. However, let me highlight that our technique does not really need retraining or fine-tuning to dynamically switch between models of different computational and memory footprints. Next, we have federated learning specific techniques aiming to bring the whole system workload down, either by means of carefully selecting the clients or by controlling the amount of operations allocated to each client and potentially dropping slower ones, or even controlling the aggregation scheme. Issues in this family of approaches may include a potential uniform workload allocation that limits the model complexity to the weakest participating device. Bias is due to the exclusion of certain clients, or in the case of controlling the amount of iterations at each client, that the initial model might not even fit in memory in the first place. So controlling the iterations when it doesn't fit in the first place is kind of redundant. So last, there are techniques aimed at bringing the communication, or both the communication and the local computation, down by means of reduced precision, pruning, or even random dropout. However, some may impose unrealistic restrictions for in-the-wild deployment, such as consistent client participation. This might be possible in a control or smaller scale deployment, but would not be possible to scale to millions of devices out there. Last, there are also techniques such as federated dropout that adapt computation to the weakest device, losing on the potential of more capable ones, and essentially not treating the problem of heterogeneity. So the research question that we're posing and we're trying to answer is, how can we tackle strugglers in federated learning in a fair and scalable manner? And to this end, we present FjORD, a system that enables heterogeneous devices to participate in the federated learning process by dynamically adapting the model size and thus the computation, memory, and data exchange sizes to the available client resources. So first, let me introduce our ORdered Dropout method, which FjORD is based upon. So ORdered Dropout. It is an importance-based pruning mechanism based on sample-nested submodel training. It enables the extraction of nested submodels at runtime without the need to retrain. ORdered Dropout is parameterized by the values of the dropout rate, which is actually the kept rate, which is taking values in the 0 to 1 interval. And then it's the set of candidate values that P can sample from, and the sampling method, of course, itself. In our work, we use discrete and uniform distribution of p-values, as it will be discussed later. So in the centralized setting, ORdered Dropout works as follows. So for each batch inside an epoch, we sample the p such that it takes the values from what we have defined, and we construct a submodel fp as follows. For each layer L with a width of k L, the submodel has all the neurons or all the filters, depending on the nature of this layer, with index 0 to the ceiling of p multiplied by kl minus 1 included, and the rest, along with the redundant connections, pruned away. And then we train this submodel with or without knowledge distillation. And in the case that we use knowledge distillation, we have the teacher being like the full model, the vanilla model that we start from, and the student being the sampled submodel that I just described. So comparing our technique with ORdered Dropout, the latter is primarily, with random dropout, the latter is primarily aimed at regularization and drops neurons stochastically at random, instead of adjacent ones that ORdered Dropout does. This leads to irregular sparsity patterns that off-the-shelf linear algebra packages do not really optimize for by default. So how does ORdered Dropout translate in terms of operation and parameters? Analytically, we see that for fully connected and convolutional layers, the operations are dropping quadratically with respect to the p-value, and linearly for bias, normalization, activation, and pooling layers. For the network we used in our experiments, this translates to the numbers on the rightmost table. You can see, for example, that ResNet 18 can move anywhere between 23 millions of floating point operations to 555, and between 456 thousands of parameters up to 11 million. And the same kind of applies to the other networks that we tested upon. So in terms of parameterization, ORdered Dropout is mainly parameterized by three things that I mentioned before. First, it's the dropout rate, or better, non-dropout rate, that defines the submodel's width and thus its footprint. This can be uniform across layers, which is the case in our experimental setup, or uniquely selected per layer. The latter, though, greatly expands the search space, kind of explodes it, and thus might be more appropriate for NAS techniques to solve. Next, we have the set of candidate values, capital P, that P takes values from, and essentially defines the granularity of submodels. The values of the set are discrete by design and should reflect two things: the width of the network and the number of device tiers out there in the wild. Last, we have the sampling method of P over the set of candidate values capital P, which defines the frequency that the submodel is picked for training. A uniform sampling method is to be used, for example, for similar device representation per device cluster, whereas the non-uniform alternative can compensate for skewed device participation. So here we present some preliminary results of ORdered dropout operation in the centralized setting. The setup is that we have a uniform distribution of p-values from 0.2 to 1 with 0.2 increments. The baselines is single end-to-end trained models at specific widths defined by the p-value distributions. These are represented by dots as one cannot really move from one model's width to another without retraining. Next, our technique is depicted with the orange lines and is a single network of nested structure that can dynamically move between operating points without the need to retrain. We can see from the above graphs that the DNNs trained with ORdered dropout behave on par with the baseline across data and modalities, but with the added benefit of variable footprints. And you can see that the degradation in performance, in accuracy, is less than 1 percentage point. I also briefly mentioned before, like in a post-it note, that ORdered dropout exactly recovers SVD. We theoretically prove this for a linear mapping of two fully connected linear layers with no activation or biases. The proof can be found in the appendix of our paper preprint. Moreover, we also empirically show that ORdered dropout can recover SVD by generating a 5x5 random matrix, compute its SVD, and having a 2-layer neural network trained over 10,000 iterations with ORdered dropout. As seen by the leftmost graph displaying the Frobenius norm between the best K-rank approximation of A and the best ORdered dropout submodel, it converges and it recovers SVD. Thus, we also empirically show our previous claim. When it comes to applications of ORdered dropout, one can use it in a train once, deploy everywhere manner for adaptive inference over devices of different capabilities or computational loads, or over varying up specific execution requirements such as latency deadlines or accuracy constraints. Of course, ORdered dropout can be orthogonally used in the realm of federated training to elastically scale computation on the based on the client's capabilities, as we shortly see next. Now I'm going to move towards ORdered dropout in the federated learning setting with FjORD. So Sam, if there are any questions, please let me know now. It will be a good time before I move forward.
So now there are no questions in the chat, but great. Yeah, awesome. So please feel free to pose your question and just raise your hand if there are any questions. Okay, great. So maybe you can just wait like 10, 20 seconds. Maybe people will have some questions. If not, then we can move on.
Yeah.
Okay, so it seems that it's clear. So please go ahead.
Great. So FjORD. FjORD stands for Federated Learning with ORdered dropout and is exactly what I previously described. Standing on the shoulders of ORdered dropout, devices of similar capabilities are clustered together, and each cluster is associated with a maximal p-value. This translates essentially to the widest submodel that this device tier can handle. This clustering can be done either heuristically or via benchmarking at first participation during the training process or incrementally. But this is outside of the scope of our work with FjORD. Moreover, this Pmax value can reflect the dynamic computational load of the device due to other tasks running simultaneously on the device. This way, at training, the participating clients only receive the maximal submodel that they can handle, not the whole model. And at each batch of a round, the device samples a different p-value lower or equal to Pmax, leading to computational and memory benefits, as seen in the table that I also showed before. Upon training's end, the only need is for the clients to send the maximally uploaded model, which is like the max of the p-values that were sampled, which is less or equal to the Pmax value. And thus we also have the respective upstream bandwidth savings. So training in FjORD looks like the algorithm on the left side of the slide. I want you to pay attention to the sampling process of the client, which selects a p-value equal to Pmax, and that the server only updates only averages the updated parameters from its client in a normalized manner in order to account for the number of clients that actually update this part of the network. In the case of knowledge distillation, we're using as the teacher the maximal submodel supported by the device instead of the full model in the centralized setting, and the student remains the sampled submodel at that round. Also, we have some let's say contributions on the permutation invariance. So coordinate-wise averaging of updates may have detrimental effect to the global model's performance due to permutation invariance property of hidden layers. Current techniques solve it by quite expensively by doing neuron matching. However, due to FjORD's nested structure and natural importance ordering, it is able to limit the effect of permutation invariance by design. So again, if we have any questions, this would be a good time to go ahead with them. Otherwise, I can move to evaluation results.
Okay, so far there are no questions, so please move on.
All right, that sounds good. All right, so next I'm going to present some of our results of our evaluation of FjORD. First, I'm going to describe the experimental setup and then provide some comparisons of FjORD with baselines, the performance with using knowledge distillation, as well as the scalability and adaptability of our system to different device clusters and distributions. So we implemented FjORD on top of PyTorch and Flower. We ran our training experiments on a private cluster with NVIDIA V100 CPUs over 3 datasets illustrated in the table on the right. 2 of them are vision classification tasks in the IID and non-IID setting, namely CFAR and Feminist. And the next one is on next character prediction using the Shakespeare dataset in the non-IID setting. You can also see the number of clients of each of the datasets participating. In general, we sampled 10% of the clients at each round and allow for up to 100 simultaneous clients on one node. Thus, clients can support identity over provisioning for supporting larger datasets and user bases. We compare FjORD against the following baselines. First, we have Federated Dropout by Sebastian Caldas from CMU, which is internally using random dropout and channel reordering to save computation and memory in the federated setting. However, it assumes the same dropout rate for all devices, which is limited by the capabilities of the slowest participating device. To this end, we propose an extended version of Federated Dropout, which name comes from that, extended Federated Dropout, and adapt the dropout rate to each of the device's capabilities. Last, we also combine the extended federated dropout variant with FjORD to allow for us to go to a higher Pmax value by partially leveraging random dropout. So to explain,
there is one question in the chat. Awesome. So I'll try to unmute Rafi.
Yeah. Sure.
If you can ask yourself, please.
Hello. My name is Rafi. And your presentation was really great, but I have more kind of general questions. Mm-hmm. Like I'm new in the field of embedded AI. So like on-device inference currently I'm studying. But it feels like when I am looking at the different research paper, I'm following your research for quite a long time, over 1 year. So like on-device inference is kind of matter of past, and now everybody is focusing on on-device training. Is it right, or what will be the direction or the research direction for the on-device inference if anyone is start in that field, or do you suggest me to also focus on the on-device training at the same time if I am new in this field? If you have any suggestions.
So in general, I would say that these are not mutually exclusive, and the fact that we are moving towards on-device training does not exclude that we're also doing inference. If anything, I would say that we're doing, let's say 90% of the time we're doing on-device inference, and maybe 10% of the time we're doing on-device training. It's just that we are changing the way that we have been doing training due to hardware becoming more and more, let's say, capable on devices. And also like the privacy preservation of user data becoming a higher priority in the agenda of companies or like users, right? So these are the main factors that kind of create an urge to move towards training, either being like on-device training or federated training or any kind of distributed training, which could include, for example, split ML, right? I don't know if I answered your question, or I don't know if we have any other questions. Sam, please let me know.
Yes, so there is one extra question, but I don't know, like whether Rafi are still unmuted. So maybe was the good answer? Okay, so there is another question by Shu. I'll try to unmute you.
Hello.
Hi.
I'd like to know more about this last technique you mentioned, the FjORD with EFD. Can you explain more on it?
Sure. Let me go to the next slide, and I will give you like a good analogy. Great. So let me move on, and maybe if we have further questions, Sam, you can let me know. Next. So EFD, extended federated dropout. Let me give you a cheesy analogy here. Imagine, for example, that the model is a chunk of cheese, and submodels of smaller slices are smaller slices of this cheese. So random dropout can be thought as holes in this cheese chunk to reduce the total weight, and the amount of holes can be selected according to the device capabilities in extended federated dropout. In the case of FjORD with extended federated dropout, the goal is to have a specific weight of cheese. This means that it has a specific footprint that we want. The way to achieve this is either to have a smaller piece of the whole or a slightly larger one with holes in it. This is exactly what FjORD with extended federated dropout is doing. It attempts to push the size to a higher tier and is trading off some of its internal structure. And please note that this technique is also widely used in mechanics to craft lightweight and structurally rigid materials, and not only in cheese making. I hope this made it a bit clearer to the audience. So in this slide, I'm going to present some expected results for completeness. We have the theory datasets and that I mentioned, and we showcase that extended federated dropout strictly dominates federated dropout by a significant margin across modalities and datasets, as expected due to its adaptive dropout rate. Thus, onwards, we only provide comparisons with extended federated dropout. All right, so if everything is clear, I can move on with the comparison of FjORD with the baselines out there. So
there is a question.
Yeah, go ahead.
Yeah, I'll try to unmute Min. Okay. So Min, please go ahead. Your question.
Hello, thank you for presentation. I'm confusing the relation between dropout and SVD. As I understand, SVD is for a linear zebra, right? And could you please elaborate more about it?
Yes, are we talking about now the proof that I mentioned before about our theorem, or in general, what is the difference between SVD and ORdered dropout?
Yes.
All right, so SVD in general tries to decompose a matrix into the singular values, and in an ordered manner that it extracts essentially the most important parts, the most important components of the matrix representing, for example, a neural network. Mm-hmm. So when it comes to pruning, in this case, ordered pruning, you can see a parallel. If we kept, for example, certain parts of the network or certain parts of this matrix, we would essentially like to have the most important ones, right?
Yeah, yes.
So this is the parallel between like the SVD and the ordered dropout.
Okay, thank you so much. I'm clear.
Of course.
Yeah.
Some, I guess that we don't have.
Just continue, please. Yeah.
All right. So coming to FjORD's evaluation, in this slide, we're comparing the performance of FjORD against the aforementioned baselines. The setup is that we have 5 uniform device clusters of p-values from 0.2 to 1 space with 0.2 increments. And these device clusters are uniform. You can see that FjORD trained with knowledge distillation in the blue line and with extended federated dropout in the orange line. Last, you can also see the extended federated dropout represented as red dots, once again signifying the end-to-end training. Essentially, this means that dropout is used for all devices that are in lower tier than the dot representing the model, and the ones that are above it in terms of cluster participation, they can already run this model in terms of their capabilities. So results show that FjORD outperforms extended federated dropout, and by extension federated dropout, by a significant margin. On the one hand, FjORD with extended federated, on the other hand, FjORD with extended federated dropout does not yield better results, illustrating that one would rather use a lower Pmax value than utilize a random dropout to move to a higher Pmax value and a larger submodel. Last, we see that FjORD converges faster and smoother to a better result across datasets in the bottom graphs over 500 global training rounds. Next, we also performed an ablation of knowledge distillation to see what it offers actually to FjORD. The setup is that the Pmax submodel is the teacher, and we're doing a full forward and backward pass with the hard labels on the Pmax submodel. Moreover, we use the P submodel as a student, and we do a forward and a backward pass with only the soft labels. You can also see like the cost functions on the left side of the slide. So please note that the Pmax value is selected to account for the extra forward and backward pass of the Pmax submodel. Results indicate that on average and above P equals 0.4, knowledge distillation improves uniformly the performance across datasets. However, for P less or equal to 0.4, this was not clear, and especially for vision tasks. This might have been a side effect when we were doing the hyperparameter search, because we were picking the best on average. So that means that the best design would be the average of the specific accuracies of the submodels, which might have skewed the results, and we could look into a weighted sum instead of an average. Also, it could indicate that the smallest submodel might not have the capacity to effectively learn from the soft labels of the Pmax submodel. We plan to investigate further with different knowledge distillation hyperparameters, and these are namely like the distillation temperature and distillation alpha, which is the relative weight between the soft and the hard labels. So last, we evaluated FjORD's behavior in terms of scalability to more clusters of devices and adaptability to different device distributions per cluster. For the scalability experiments, we test against two setups. The first one is that we have been using until now, and that is five uniform clusters with p-values from 0.2 to 1 with 0.2 increments. And the second one is using 10 clusters with p-values ranging from 0.1 to 1 space in 0.1 increments. Our results on the right-hand side indicate that FjORD is able to sustain its accuracy even under denser p-values, which represent essentially more clusters of devices out there. In terms of adaptability, up until now, we have been using equisized clusters of devices. Thus, in the case of 5 clusters, we had 20% of client allocation in each of these device tiers. Now we compare against the case of drop scale equals to 0.5, which means that we have the participation of devices in lower tiers and allocate the extra devices on the highest tier. This essentially means that we have 10% participation in the lowest 4 clusters and 60% in the highest one. The reasoning and intuition behind this is that essentially most of the devices will be able to run the global model in its full form out there. Results indicate that FjORD does not significantly degrade the performance of smaller submodels in the presence of more high-tier devices. However, as the high-tier devices are more represented in this scenario, they can expectedly boost the performance of higher p-values since they are significantly more frequently sampled in the training process. So, do you have any questions?
Okay, so for now there are no questions in the chat.
All right. So some limitations for our system. First is, or like the evaluation. So as I said before, we tried uniform p-value sampling across layers for tractability. So that means that different layers inherit the same p-value that is globally defined. We can do this in a different manner and have a different p-value according to the position, for example, or the type of the layer. But this would blow up the space, and we would rather use NAS techniques in order to be able to explore the hybrid p-value dynamics. However, our uniform p-value sampling does not hurt the generality of our solution. Moreover, there is the assumption that the device clusters or the device load is assumed and the clustering is given. So this is essentially outside of the theoretical concept of FjORD. And in general, this is a system parameter that could be done either analytically or heuristically by using, for example, the device model or even the SOC model. We did the evaluation on a server and not on mobile devices, mainly because of the lack of maturity on smartphone tools to perform on-device training. This is in general a limitation in the ecosystem, but we expect that things are going to change in the next years to come because of training gaining more and more traction on device training. But even if this was the case, we did measure the gains both analytically, and we showed the gains in terms of number of floating operations and the number of parameters in the table that I showed before. Some of our future work is aimed at submodel personalization and specialization. So the goal of our FjORD's work was to create a globally good model. That means a model that performs well across the clients. However, we would like to explore the dynamics of when we have slightly different tasks to tackle between clients and the server, of course. And we would like to personalize each of the device resident networks to the task that they are handling. How would this affect the knowledge ordering of ORdered Dropout in the federated setting? Next, we would like to visit alternative dynamic network techniques for heterogeneity in the place of ORdered Dropout. So, for example, one example of this could be early exit networks, where you essentially hang early exits along the depth of the network, and you can have early classifiers based on earlier or shallower features inside the network. So instead of going towards the width dimension and pruning away width in order to create different submodels, we could go in the dimension of depth and do so. And last, I want to mention the problem of extensibility to next generation of devices. As aforementioned, we have federated training systems that are deployed, are aggregating knowledge in a lifelong manner. So that means that it's not one single training process that is handled offline and it's repeated every time that we want a different variant of the model, but we have essentially progressive incorporation of knowledge in the architecture of the model. So as this happens, you might have next generation of devices coming up. That means that the cluster allocation might change not only towards having like the cluster participation, but creating a new cluster that is even more performant than the previous ones. And we would like to see, we would like to explore techniques that enable us to expand both the clustering and the p-value allocation, as well as the architecture in this domain. So in summary, I presented ORdered Dropout, which is a technique for nested ordered knowledge representation that enables dynamic subnetwork extraction. I've presented FjORD, which applies ORdered Dropout in the federated training setting to tackle system heterogeneity in a fair and scalable manner. And FjORD is shown to perform better than the state of the art and adapt to different device distributions found in the wild across datasets and modalities. Some acknowledgements and a shout out to my wonderful collaborators from KAUST, namely Samuel, and from Samsung AI. And with this, I would like to conclude the talk and open everything for open up the talk for questions if there are any from the audience. Thanks a lot. Some announcements also is that in general, we're hiring interns at Samsung. We're hosting the Federated Mobile Sensing for Activity Recognition tutorial at MobiCon 2021 in, I think it's October time, end of October. And we're planning the second distributed ML workshop at Connex 2021, which is in December time. Thanks a lot.
Thank you, Steve, for your great talk. And okay, so if you have any question, so please just raise your hand or post your question to the chat. Okay, so I'll start with one quick question. So maybe can you please elaborate? So if one talks about dropout, so people usually think about dropout as a regularization technique that is not applied for the inference. So can you maybe elaborate on the what is difference for the ORdered dropout and maybe how that can be applied for dynamic inference and how is it applied for the inference?
You mean in the federated training? Sorry, in the federated dropout.
For the ORdered dropout, how that's applied.
Right. So there is a distinction between random dropout and ORdered dropout. Random dropout is dropping neurons or channels randomly, and it's mainly used for regularization. Our technique might be called ORdered dropout, but essentially it's a pruning mechanism. A pruning mechanism that is based on the fact that we train the model in such a way that it orders the representation in a nested manner inside the network. So what this means is that we have the global model that essentially incorporates submodels, and each of the submodels incorporates other submodels. This is the nested nature of our solution. The way that we're training this is by means of sampling. So that means that at every round inside an epoch, so at every batch essentially that goes through the network training process, we are sampling a p-value so that we forward and backward propagate across the weights of that specific submodel, and across many rounds and across many epochs of training, you essentially create this nested structure inside the network. That means essentially that the whole model looks as if it was beforehand, like the vanilla variant. But the added benefit is that we can extract dynamically different operating points of this network by means of extracting the submodels without the need to retrain. That would not be the case, for example, in let's say weight pruning, because normally you could have the need to fine-tune the network in order to gain back some of the lost accuracy. In general, there is a family of solutions. There is a whole family of solutions that are taking advantage of the latency versus accuracy trade-off. But certain solutions belonging to this family of approaches do need to fine-tune after doing this step of moving to a lower footprint model. Yes, and yeah, again, I guess that it's clear with random dropout where we stand. Random dropout was never really created for this manner, and it was the Federated Dropout paper that kind of approached this by also means of channel reordering and thus being able to lower a bit the memory and compute footprint of the model, but it had the limitation of assuming the weakest device in the chain in order to treat the problem uniformly. Yeah.
Thank you for the great answer. There is another question from Anupam. I'll try to unmute you. So please go ahead.
Hi. So my question is, maybe I missed it, that you said that you perform the dropout in a fair manner. So what does fair means?
Right. That's a good question. It's a fair question. So that means if you include approaches that drop essentially device that cannot participate. Imagine that you have a federated learning setup where you have devices that belong to different tiers of compute or different generations. So you have, for example, a Galaxy S5 and the Galaxy S10. These belong to very different generation of devices, but they used to be the high-end device at their time. So if you had the quite big, quite large, and this is in order to be able to have the capacity to learn the task at hand. So if you had this large model and you were to deploy it across devices, that would essentially mean either you would have to, so you would aggregate from the Galaxy S20 or 21 nowadays, and you would have to wait until the Galaxy S5 or S7 or whatever finish the training process, given that they have almost the same data, right? In order to aggregate the weights and move to the next round. That means that you would have a straggler there. But an alternative to mitigating the straggler effect is to drop the device altogether. So if you see, for example, you create essentially a deadline in the server side that says that, okay, I have over-provisioned my clientele for this round. So I would need 10%, but essentially I'm sending the global model to 20% of devices. And I'm waiting for, let's say, 10 seconds, right? If I don't get the results in 10 seconds, whoever hasn't responded, and if I am above 10% of my clientele, I will aggregate and drop the rest. If not, then I will not even aggregate, and I will just go again with the sampling round. So if you do drop these devices consistently, so the lower tier devices compared to the higher tier devices, this creates a bias in the system, right? And this is the unfair part of treating the problem like this. And there is also like the correlation with certain demographics or certain, let's say, geographic locations that might have a background of like, let's say, lower tier devices because of the cost, because of like not having access to 5G. So why would you need a latest generation 5G device? So that would essentially exclude this part of the population from contributing to the global model knowledge. And this is like creating unfairness, biasness, and bias, and so on and so forth. And FjORD, by not needing to exclude these devices, but just allocating a smaller submodel that they can handle inside the deadline, it is able to tackle this problem in a more fair manner.
So it's more like adaptive, right? So you're
Yes.
saying it's more like adaptive, because fairness sort of goes into that different, meaning, and how do you compute fairness becomes another question. Mm-hmm. Okay, thank you.
Cheers.
So now everybody is actually able to unmute themselves. So if you have any question or comment, just feel free to unmute and ask Steve.
Hello, I have the last question, maybe. The dropout strategy is applied. I mean, your proposed one is applied for all the mobile devices, or only at the decentralized one?
Sorry, can you repeat the question? I don't think I got it.
Yeah, yes. Your proposed dropout strategies is applied for all the devices, or only at the decentralized server?
So essentially, the technique of ORdered Dropout is more general, I would say, than
Yes.
Federated Learning, in the sense that it can be applied to different scenarios. So one scenario like this was that we could train in a centralized setting, or whatever, we can train in whatever manner we would like. And then at inference level, we can dynamically adapt the footprint of the model in order to do inference at different devices of different capabilities. This might be mobile phones, this might be IoT devices, it might be whatever. It might also be computers. This also can reflect not only the capacity, the static capacity of the device, but it can also have like the dynamic load incorporated, or even the app-specific requirements of the application. So imagine, for example, that you have an application such as, let's say, mobile health, right? And you want to classify, for example, the activity that the user is doing. And you cannot obviously do this classification in, like, let's say, 10 minutes time. You might need the results at a specific point, like this being like the deadline. And you might also want some actionable results, even if they are less accurate, let's say, and you could refine these later on. So at the inference point, ORdered dropout could be such an adaptive mechanism that does that. Now, apart from this use case, you have also the use case of training this on device. And you have the problem there, you also have the problem there of heterogeneous devices that exist, right? Which is either equally or even more amplified in terms like they do contribute more to the training, to the training of your network. So that means that you could leverage the ORdered dropout technique in order to be able to train in such a manner. So compared to different techniques, for example, that use adaptive dropout, these techniques at training time might not have the benefit of training with different footprints. However, our technique can do that also for training and for inference, right? So this is one of the differentiating points with other work out there, such as, for example, early exits.
Yeah, thank you so much. Yeah.
Yeah, I see a question, but this is a private one. But in any case, the Mobicon 2021 is GitLab area.
Okay, so maybe let's wait another 30 seconds, or maybe if there are any other questions.
Hi, I have a question. If I can ask one.
Of course.
Okay, so thank you very much for your talk. First of all, I have a curiosity about the combination of continual learning and federated learning, actually. So I don't know if you're familiar with the topic of continual learning task, but I mean to consider both domain distributions and class-based changes over the time, but you want to do it in a federated learning setting. So basically you want to update your model in order to recognize new domains, but also new, let's say, classes, for example. I think the approach you mentioned, you proposed, actually could be beneficial also for this purpose, because future tasks, such as an addition of new classes, may need to have some capacity which is not being used by the network itself, right? So yes, if you prune your network, you do, okay, you're doing it maybe for the sake of compression, but you can also maybe do it for preserving network capacity for future tasks, right? So my question is, have you thought of doing something like this in the future, or if you can elaborate further on this?
Yes, that's a very good insight, Umberto. So yes, essentially we're moving toward, like as I said before, regular centralized training is kind of happening in snapshots, right? You have a data set, you train your model, you deploy it, you do inference, and then at the next point you kind of have like the next generation of the model deployed. However, in a federated setting, you kind of invest in a lifelong learning manner. So that means that you have devices out there that behave in the wild. You don't have them controlled in any manner, and you might not even be able to model like the distribution of, let's say, classes, the distribution of features, etc., etc. And this might actually be temporarily changing. So that means that in time, they might not be static. This could have impact on the dynamics of the network. So you can look, for example, in catastrophic forgetting effects, or it can have effects in terms of where the specific, let's say, clientele is focusing on. And this is the part of like having multitask federated learning. It kind of goes towards. I see this as very relevant in terms of like expanding the network towards new knowledge or new labels coming up. This could also be like both in the learning setting, so you get new data, new distributions, new labels, but you also get like the new devices that I mentioned in the presentation. So the question is, how can we change or expand the network architecture in a way that it preserves what it learned, but it also expands towards the new knowledge? And I see a central, let's say, a core technique, at least how we approach in the way that we approached our work at FjORD. I see distillation being central there, because as I aforementioned, we do the distillation on the Pmax value, and then we distill this knowledge to lower submodels, right? So if you could have like this on an expanded version of the width, and then move or distill knowledge towards the smaller submodels, I guess that this would be very promising. But this is a hypothesis, so yeah, take it with a pinch of salt.
Yeah, sure. Thank you very much for elaborating on this.
Thanks for the question. Thanks a lot.
Any other questions or comments? Okay, so it seems that we are also out of time. So thank you, Steve, again for your great presentation.
Thanks a lot, Sama, for the invitation and the time.
And thank you, everybody, for tuning in.
Thank you so much.
Thank you.
And see hopefully all in the next Welcome. Have a nice rest of the day. Bye-bye.
You too. Bye.
Take care.
Thank you. Bye.